So let's imagine some platform that allows you to modify its domain by adding new entities and connection between them, create highly flexible views that represent the data in this platform, and also create extremely flexible automations that can generate unpredictable and high transactional load. So in terms of flexible domain, which it means that you can create entities, connect them with one-to-many, many-to-many relations, create attributes for them, and all of this is projected on the database level. On top of this, you can create different views like two-dimensional boards, and level hierarchy lists, timeline views that represent the data, both custom and native, and they can be configured with really flexible filters on different sortings. Filters can be use links between entities, like for example, I want to show on this board user stories that have tasks which can be which were assigned to some particular person in the system. Then sometimes because of this you get something like this as a query for performance investigations. Not always pleasant, but sometimes you start to see metrics and you feel like a Neo. And also on top of this, we can have automations that react to the events that are happening in the system, like for example, some data changed or some field of particular entity change, and we can create a custom business logic in the system that can be expressed via like custom JavaScript or some predefined UI actions that are already implemented. And we have some formulas which we can configure to maintain values for particular fields. So in total, on the platform, we have 4 axes of happy living. So we have custom domain, we have ability to modify data unpredictably and frequently based on our custom automation. We have extremely flexible engine, and we have a lot of data, like millions of records, hundreds of gigabytes of data per tenant. So yeah, to be honest, it's not the best for access you want to see in requirements for data storage. And you can ask questions, either how we can live with all this stuff. And I asked myself, and in general, yeah, probably there is no hope. Presentation is over, so let's eat pizza. Yeah, and I'll go to my shrink and with this presentation, and maybe he will advise something. So yeah, that's all. Yeah, but yeah, okay. I guess I'm not the worst actor. Okay, there's always hope. Yeah, and you should believe in yourself, no matter what. Um, so, of course, we can ask questions. Well, we can actually implement it other way. We can redefine the business requirements, collect them for future 5-10 years so that those business cases will be valuable, implement new version of the platform with some restricted and predictable usage patterns, spread our 4x's among different types of specialized storages and so on, and explain users why they cannot do some things they were able to do before, migrate the data, and live happily. But even we will do this someday, it takes time, and while this, we still need to maintain all this complexity and predictability we have. So right now I will describe some Microsoft SQL Server specific tools that we can use to diagnose issues. And of course, having some distributed tracing system like Datadog or good logs that allows you to bind particular query to particular piece of application that caused it is always useful, but here I will be focusing mostly on SQL Server. So in general, we usually have two cases when we know what is the problem, like some, I don't know, particular UI component doesn't work, and we have particular queries that doesn't perform so well, and the cases where we don't know what exactly is the problem. So in case we have a problem, so we usually have some query, and we usually can get it execution plan. And it can be quite rough to analyze it at first, but there are some things that we should pay attention at first for it. So execution plan in general, it in terms of the way it's like interpreted, it goes from the right to the left. In terms of the way the data flows, actually it goes from the left to the right, and it contains many operators like types of joins, like types of different seeks and scans of different indexes. And the first thing we should pay attention to it is the cost of particular operator. So it's a relative value, rather abstract, that includes some compute, some I/O, some memory, and it's relative in terms of scope of the entire query. So it shows you how much resources particular operator either are expected or actually used within execution of particular query. So it can be useful, but sometimes on big queries, the cost itself can be spread it around the execution plan, and you have one, two costs, and it's not really clear in terms of getting to the root cause of the performance issue. Then there are data pipes, and they are more universal. They actually show the way the data flows in the query when it's executed, and on all tools usually that are displaying execution plans, they are visualized accordingly to the amount of data that is being transferred from one operator to another. And in general, we want to achieve the state when those databases become thin as soon as possible, like when we're moving from the left to the right. And that means they all start from the scanning or seeking some index or a table in case there is no any index on the table, and our goal to make those scan as much productive as possible in terms of filtering out the data. Then we should pay attention to for scan operation of the indexes, because they're not always bad, but they usually I/O intensive in case they're scanning a lot of data and the predicate is not efficient on them. And they are a sign of usually a big I/O operation, which means that something is being read from the disk and loaded to the memory, which means that something also can be pushed off the memory. And we will discuss more the issue and some tips regarding memory pressure later. So also important thing is statistics, because SQL Server, when it's builds and analyzes the query, it uses the statistics on particular fields, and it's collected for all index fields, and it's also it starts to collect for all fields that are using in where or having statements in the queries. And in case the statistics is not updated, obviously it can lead to wrong decision making when the query is executed. And usually people tend to forget about it, but especially in highly loaded and dynamic applications, like it's may think to alter the default behaviors of SQL Server in terms of managing the statistics. And memory usage, you can find it on the root. For entire query, you can find it on the properties of the root operator in the query plan. It's also important to see whether the query using a lot of memory, because it's usage of a lot of memory can lead to performance issue not only for this query but for other queries on the server. So that's the summary: data pipes, costs, memory usage, scans. So let's move on to the situation when we actually don't know what is the problem. So, and one of the coolest feature, I think, SQL Server is query store in general. You can configure it for a database, configure its size, retention policy. The thing is that you can it collects all the queries by default that are being executed on the server, and you can get the statistics or for these queries for particular time range, and you can have the statistics. You can get top 25 queries that used CPU within particular hour or day and so on, and it's extremely useful in terms of analytics when something goes wrong with memory or CPU usage, and other stuff also, like disk access and so on. So there are a lot of stuff that can be addressed here. Usually it's most used are CPU, memory, wait times, but also you can see there regress queries can be useful. Everything can be useful in narrow cases, but usually top resource consuming queries, regress queries, and wait statistics are the most useful. So like just as example, you have excessive CPU consumption, maybe it's sporadic during certain times, and you can just configure query store for your database and review the queries for this particular data range. Same for memory issues, and it also can be configured and set up via script, and all data that is stored can be accessed via scripts through the view and tables. So even if you don't have direct access to the database, you can probably configure gathering this information via some automation. The next thing is extended events. So if some of you worked with SQL Server, probably many used Profiler. It's somewhat similar but more efficient, because Profiler is has rather big performance price when using it on the server. But this one, extended events are quite efficient in that regard, and you can just configure a session and collect almost any events that are happening on the server, like query execution, particular query execution filtered by text or statement or user or database, logs, blocking deadlocks, and so on. And you also can access it via queries and collect it indirectly without direct access to the database. Activity monitor, it's pretty simple, but it's more suitable for situations when you have some live problem and you need to fix something that is happening right now, and it shows you actual state of the sessions. All the data also can be expressed here via queries, but in terms of simplicity, sometimes it's simple just to open it and see something that, for example, stuck for some reason because someone did not configure timeout properly or something like this. So yeah, that's the summary, and let's move on to some solutions and tips and problems of different natures that we can face in flexible environment. So the first thing that I would like to address is data separation by nature of the data. It's doesn't seem like that obvious at the first time when like you configure some and the data set is not so big on the server, but when um, you start to get in data sets more than like 300 gigabytes, 30 gigabytes, such things start to kick in, especially if a server is used in a multi-tenant environment. So what it means that, for example, if we have some uh, tables that reflects entities in the database, like user stories, it's better to separate, for example, string data from the data that is responsible to store for storing references to other entities, simply because like usually those references are used more widely in terms of filtering and grouping the data, and such separation makes it's more easy to read this data from the disk for the server and to store it in memory for a longer time, which means like more performance and better performance. Um, the second thing I'd like to address it's data separation by schema changing ability. What it means, like as I mentioned, we have ability to configure custom properties, custom attributes for entities, and we can and those all of this is reflected on database schema, and um, it's better, and we have such thing as schema stability and schema modification logs when we're doing such things on the database level. And schema modification log basically blocks the access of everything that takes schema stability log, and schema stability log is taken always by all select queries that are executed. So in case you modify particular table, it's while modification operation is not completed, it's not accessible, and basically it's unavailability problem. So in order to reduce the scope of the log, it always makes sense to separate the dynamic elements to the separate tables, though the main parts of the application could still function while schema is modified. And the second tip is like uh, also about using only nullable columns for like when we're talking about dynamically added elements to the schema. Like, so unfortunately, if we are not using the nullable columns, we have to populate it with some values when we're adding them. And when you have, for example, 25 million records in some table, it takes quite a time, and we should just spread if we need this population. So we need add column and then have some long-running process of population of this column with some default value if we need it. The third thing also related to modification of the schema. Basically, by default, SQL Server has, for example, 1024 columns limit for each table, but this limit is not even a problem, because actually practically we have much lower limit because of other nuance of the SQL Server. So each row in the table that is stored, each data that is stored per row in the table should not exceed 8 kilobytes. So that means if you have some row in the table which will exceed this limit, you will not be able, or reaches this limit, you will not be able to modify it until you nullify some columns. So effectively, having more columns just raises the risk of reaching this limit, and effectively, like from the practice, usually your actual limit for the table in terms of column is 300, and if you need more, you just share it to the next table and link it to the this table. So it's like that, unfortunately. Um, Another tip, like foreign keys, like it's really cool to have the consistency of the data on the database level. Unfortunately, it has a big performance trade-off. It blocks you from using some performance improvement features on the server, like memory optimized tables, partition tables. It extends scope of schema stability log taken when you select from the child table. It also takes schema stability log on the parent table. Unfortunately, it does not work so well when you have a lot of data, and it's better to maintain data consistency not with foreign keys but on application level. Okay, let's move on for query optimization. So the simplest case we have usually is when we have some query which has stable shape and stable ordering, stable filters. And usually for that case, there is nothing better than standard index that can express the data and shape the data in order to make some this query execute efficiently. The problem with standard indexes is that, as you can see, even from their definition, they have columns defined in certain order, and this order is actually important for the index efficiency. And also every column has its own ordering, and this is also important for index efficiency for particular query. So this optimization is quite easy to break, and it does not work in case any user on your environment can just change the query easily, and your optimization will not work anymore. So, but there are some use of actually standard indexes, like for large tables, for example, you have some table with historical data that weighs like 100 gigabytes, and you have some subset of fields that are actually widely used in filtering, in querying the data. You can, it's like doesn't make sense on the first glance, but you can create actually similar index that not indexes but includes the columns that are more widely used and that are more compact than all columns in the table. And it's can besides improving the initial query that you were doing it actually can improve the performance of the entire server, because right now there will not be giant scans of your giant table that will be pushed off all data from the memory of the server. And it's actually like one thing that actually helped me several times to solve some deep performance issues on the server. It's quite simple. Like basically, you create the same index as foreign key, but it's just more lightweight and quite big. Helps quite big. Then we have also column store indexes and batch mode, and it's like, in terms of relational databases, it's new feature probably. I think in SQL Server it's appeared in maybe around 2012. Overall it's an old concept, but on large data set, specifically for when you have a lot of queries with aggregations, it makes sense just to put the columns into column store index, and they are less sensitive they are not sensitive to the order, so it doesn't really makes any difference what order you define the index definition. So it basically splits the data set into segments, and it's more comfortable for batch processing, and it makes SQL Server to process the rows in batches. It's not as efficient as classical indexes when you need to search something by key or like search narrow subset of the rows. But when you have a lot of data and you don't know how it will be queried, it's quite more efficient than classical indexes. It's actually only solution because you cannot have all variety of classical indexes to cover all the cases of the some GraphQL like API. And the last great tip I have is basically related also to column store. There you can also convert entire table to column storage, which will provide you indexing for some indexing capabilities for all columns in the table, and it also will compress the data really significantly. And for some scenarios, like it's especially effective in case, for example, historical tables that have, for example, a lot of repeated values, or sparse tables that contain some custom attributes that are defined by users, but usually they're for majority of the rows they can have null values or the same values, and you can just by changing the type of the storage you can compress the data 5, 7, 10 times, which makes it more easier for SQL Server to read it, to load it to memory, and to process it. I think this is the end. Yeah. Thank you for attention. Yeah. And any questions?